All right, people, it's me once again. My name is Richard, and it has never changed. So today we're doing a little bit of fillings. I forgot to finish bonding and chemical interaction. So today we're gonna fill that in, get that done and dusted, and then we move to compounds and stoichiometry, and hopefully we finish that today so that we can move to the chapter 5 of the MCAT chemistry review. So for the bonding and the chemical interactions, for the bonding and chemical interactions, we got to a point where we call polarity. Now, talking about, let's say, polarity of molecules. When we talk about the polarity of molecules, what we are trying to say, or what we're trying to mean, is that how much charge is within a molecule. And as a rule of thumb, non-polar compounds or non-polar molecules will always be non-polar. But for polar molecules, they may be polar or they may not be non-polar. Why am I saying this? Atoms of different electronegativities interact with each other. So if they are the same atom interacting with each other to form maybe a dioxide gas or ozone, like anything, like a dioxide gas, right? Let's say oxygen or nitrogen, something like this, then there wouldn't be any polarity because it's two atoms of oxygen and both have the same electronegativity. But if atoms of different electronegativity interact with each other and the difference between their electronegativity is greater than 0.5 but less than 1.7, the compound is said to be polar, right? But then polar, as again, the compound, the electronegativity difference telling us that the compound is polar doesn't necessarily make the compound polar. But you have to take into a consideration or into an account the molecular geometry of the compound or of the molecule. Take this molecule for instance, CCl4, right? Carbon tetrachloride. This molecule, there is a vast difference between the electronegativities of carbon and then the chlorine atom over here. But since this molecule has a tetrahedral shape, if you draw a tetrahedral shape, you have your carbon here, the chlorine here, the chlorine here, the chlorine here, and then a chlorine here, right? So if you draw out the tetrahedral shape, you're gonna find something like this, right? In 3D space. So these atoms are of different electronegativity, and the one with the bigger electronegativity will pull more of the shared pair of electrons towards itself. So once it pulls the electrons towards itself, it renders these ones to pick up, a charge, a partial or a false positive charge. Once they do that, you might say that the compound is polar, but this compound specific carbon tetrachloride is non-polar because the vector sum of the charges points towards the vertex of the tetrahedra, so they cancel out, right? Some positive partial charge will be pulling this way, right? And then one will also be pulling this way, so this one will cancel this one out, and one will be pulling up and the other one will be pulling down, so they will both cancel each other. So that is the polarity of a compound. Now there is a formula in calculating the polarity of a compound that goes P, which is the polarity, is equals to Q, which is the charge, and then D, line, right? That is the distance between the compounds. So that is, when we talk about polarity of a compound, that is really what we are talking about. But This polarity will lead us onto something that we do called molecular orbitals, atomic or molecular orbitals, right? Atomic / molecular orbitals. Now, casting your eye back to when we used to say that consider or an atom is a positive dense nucleus with an electrons occupying a cloud, right, around the positive nucleus, and within this cloud we have a probability or a chance of finding where an electron is, right? And these clouds are arranged into energy levels. Same thing applies here, right? When we take the atoms that are going to form a molecular bond or that are going to form a molecule, right, the electrons that orbits around them occupies states. This is quantum states, and we realize that they came up with 4 quantum numbers to describe the probability of finding an electron in a specific shell. So the first quantum number was the principal quantum number, right? The principal quantum number. And then this was denoted by the letter N, right? And it was what? The shell, the main energy level, the shell or main energy level, right? Then the maximum number of electrons that could occupy in a shell or a main energy level was 2n squared. Now we have this. This describes the main energy level where we're going to find the electron. After that, we discuss what we call the azimuthal quantum number. The azimuthal quantum number. And that was denoted by the letter L. Right, and then we say this over here denotes the subshell. The subshell, and it is not the main energy level, right? And we said the maximum number of electrons that could go over here was 12 plus 1, right? Those are the maximum number of electrons that could go here, and it describes the subshell that has a force in it. So, my main focus here would be on the azimuthal quantum number. Let's put a asterisk over here and move on to the magnetic quantum number. The magnetic quantum number. And that was also denoted by M or Lm. And that was the orbital, right? And then the maximum number of electrons an orbital could take is 4l plus 2. Right. So these, and then the last quantum number was called the spin quantum number. And this tells us whether the electron was spinning up, which is half, or is spinning down, or anti-clockwise, which is minus half. And for that, it's just the spin on the specific electron that we are looking at. So when we take this, right, I said my main focus is going to be on the azimuthal quantum number because it describes the subshell. Let me come over here. For us to find a subshell, or the formula for finding an L is basically n minus 1, right? So L is equals to n minus 1. It is the principal quantum number n minus 1 will give us L. So let's say we have an electron that we suspect that it will exist in the principal quantum number 2, which is the principal quantum number 2, right? It's azimuthal quantum number, right? Azimuthal quantum number is going to be 2 minus 1, which is going to be 1, right? Now, it's this will be the azimuthal quantum number, right? So the magnetic quantum number, which is the shell, which is the orbital, the magnetic quantum number is going to be the positive and the negative integers of this one. So we're going to have negative 1, 0, and then 1. Right? But you know, let's expand it. Let's make it a little bit expandable. Let's say the atom is in principal quantum number 3, so this will give us 2, and over here we are going to have negative 2, negative 1, 0, 1, 2. We have something like this, right? But mind you, the azimuthal quantum number that I said is my main set. When you find it to be 2, the 2 just denotes its boundaries, right? It is actually a group of numbers or a set, which it begins from 0 to the integer, right? 0 to this integer 2. So it's going to be 0, 1, 2. Now when you take this 0, 1, 2, they have something that is very, very, what is it called? Unique to them. This 0 represents the s orbital, right? This 1 represents the p orbital. And then this 2 represents the d orbital, right? When we take the s orbital, so the s orbital, if an electron is existing in an s orbital, its principal quantum number is 1, and then the magnetic quantum, the azimuthal quantum number is also equals to 0 over here, right? So that gives us the s orbital. The s orbital is spherical in shape, so the s orbital is what? Spherical in shape. Just sphere like this. And since it is a sphere, it has, if you draw a Cartesian plane through it, we're going to have the x-axis, the y-axis. And since it is a 3D sphere, not a 2-dimensional sphere, you're going to have an imaginary z-axis or z-axis, right? So this is going to be my y, this is going to be my z, and this is going to be my x-axis. So this right here is going to be my s orbital. I hope we have that one put in mind. So after the s orbital, we also have the p orbital. The p orbital is 1. The p orbital, it's not the s orbital, the s subshell. Now we go to the p subshell. The p subshell has an azimuthal quantum number with a boundary of 1, which means 0 to 1, right? 0 to 1 is just 0, 1. 1 in this case. So let me wipe right over here and then go onto it like that. So this p orbital, which has a principal quantum number of 1, let me put over here, p orbital, has a principal quantum number of 1, right? Since it has a principal quantum number of 1, it has an azimuthal quantum number of 1, right? Azimuthal quantum number of 1. Since it has an azimuthal quantum number of 1, the various possibilities for the magnetic quantum number is going to be -1, 0, and then 1, right? So these 3 over here are the sub shells of p orbital. So these 3 are the subshells. So that is why p orbital has 3 subshells, because when you expand it, it gets into this way. And those 3 subshells are unique in such a way that it's like a dome shape, right? It's like a dome shape that goes around the axis of the Cartesian plane. So let's draw one Cartesian plane here, another Cartesian plane here, and then another Cartesian plane here. But mind you, this is a 3D space we are talking about, right? So we're going to have an imaginary z axis. So this is going to be y, z, x. Same thing applies over here. Y, Z, X. Lies over here. Y, Z, X. So for the p orbital with for the p subshell with orbital -1, let's say that is the y orbital. It has a dome shape that goes around the middle of a plane like this, right? So let's say we can shape this, it goes like that. Right. And then we have this one too. Let's say it is the 0 and it goes on the x axis, right? So dome shape like an infinity, it goes like that. And the 1 is the z that goes on the y axis. So it goes on the y axis, it's going to be like this. It's going to be on the z axis. So in any point, I was going to draw this with a different marker. Sorry, let me draw it with a different marker so it's easier to visualize. Yep, so something like this, right? So with the superimposed P, the P subshell, we are going to have something that will look like this. We draw our Cartesian plane like this, and then like that. This will be the superimposed P orbital. All of them exist together in the same space, right? So the first one, the blue one, I'm not going to draw them too big. I'm going to draw them too big. Right? So the blue, let me shade this blue, right? Yep. So this will be the P, Y over here. Now for the PZ, we're gonna have it like that. Since it's going to on the Y, it's going to be behind it. So we're gonna have it come over here, something outside over here, like. Since it's going to be on its axis, we're gonna have it, yep, like that. And then it's going to also occupy a shape like that over here. And then our last but not the least, the px, which goes on the x axis, right? So that will be, and then let's say it goes that way, it is behind it, it comes this way, and it goes up. Right. So you're gonna have something like this when you talk about the P subshell, right? And it is complex because of that. See, P has three orbitals, right? And this is how the shape looks like. Very crooked. So imagine D, that's gonna have 5, and then F, that is gonna have 7. The shape is going to be complex. The MCAT scope ends at the P, the structure of the P. So with that being said, so from here, right, we could infer that some for any bond to form, right, for any bond to form, an electron existing in any of these atoms would have to, interact with similar orbitals from different atoms, right? So if we have a situation whereby there is a head-to-head interaction, whenever there is a head-to-head, we call that a sigma bond, right? A sigma bond. And the advantages of a sigma bond is that it allows the atom, right? It allows now formed molecule, because it's no longer going to be an atom. It allows the molecule to spin around an axis, right? An axis, right? So a head-to-head bond would be something like a pz orbital like this. Let's say this is a py orbital bonding with another py orbital like that, right? It is head-to-head, right? Now, if there is a side-to-side bonding, a side-to-side bond, we call that a pi bond, right? A pi bond. And then a pi bond would also be something like this, right? Something like this would be a pi bond, and the side to side. And the disadvantage of this is that it does not allow the free rotation. It doesn't allow the newly formed molecule to spin on its axis. Now, how the bonds form, whether it's side to side, being pi, or whether it's head to head, being sigma, right? Some bonds form, some orbitals overlap to form bonding and non-bonding hybrid orbitals, right? So this over here is a whole topic in chemistry called hybridization, right? But since we are doing on the scope of the MCAT, we're not really going to take hybridization on its own and then treat it. It is a very in-depth, detailed topic. But if you are doing chemistry for other purposes, it's definitely worth it to look into it. So sometimes, right, there will be an overlap, and then the overlap wouldn't form bond. It would form bonding. It will form bonding orbitals, right? Like the what is it called? The hybrid orbital. The hybridized orbital will be bonding. Now, if we say an orbital is bonding, it's basically that the orbital uses less energy, right? And it is 180 degrees in phase. So the individual orbitals that are coming together to form a hybridized bonding orbital will use less energy, and those orbitals will be 180 degrees in phase with each other, right? And by so doing, they can, synchronize and use less energy. Now, so they may interact to also form non-bonding orbitals. Now, mind you, non-bonding orbitals doesn't mean that this orbital is not fit to form bonds, right? But non-bonding orbital means that if this type of orbital is used in bond formation, it is going to use more energy, right? More energy. And then when you are superimpose the two bonding orbitals in it, they would not be in phase, right? No energy, not in phase. And if they are not in phase, what can they not do? Synchronize to perform activities that will make it energy efficient. So those are the things I wanted to add about atomic or molecular orbitals. Now let's move on to what I call intermolecular forces, and this will be the last topic that we're going to do, intermolecular forces. The last chapter we're doing under bonding and chemical interaction. So intermolecular forces, right? They are forces that exist between atoms that forms covalent bonds, right? If atoms forms covalent bonds, it becomes a molecule. Now, millions of these molecules have to come together for you to see a compound or to see a physical end product of the thing that you can physically manipulate and touch, right? Now, for these to come together, we have what we call intermolecular forces that helps it come together. It is how these various covalent bonded molecules interact with other covalent bonded molecules, right? So the first one we are going to talk about over here is what we call London dispersion forces, right? London dispersion forces. Now, when we talk about the London dispersion forces, right, what we mean is that it is a type of a ripple effect, right? A ripple effect that happens in the molecule and it spreads around, causing other molecules to also become, polarized. Now, how it happens is that if you have two atoms that are bonded together, right, each have a different electronegativity, right? As I said earlier, the one with a higher electronegativity is going to pull more of the electrons onto itself. And then once it pulls more of the electrons onto itself, it will render the rest of the molecule to take on a partial positive charge. So once they take on a partial positive charge, they in turn come close to other molecules in vicinity, right? And when they come close to other molecules in vicinity, since they are now partially positive charged, they are going to attract, right, a negative charges onto them, which will be the central atom of most most compounds. Now, when they attract them, those central atoms also inherently becomes negative charge, and their subordinating atoms become positive charge, and the chain continues and continues, making the thing bonds together. This London dispersion forces, right? It is the weakest of all the forces. So it is the weakest of all the forces. And then that is one. And then number two is that it causes the molecule itself to have a low boiling point or melting point, because it is the weakest of the other forces. And sometimes in some other books, you'll see it as they call it weak van der Waals forces, right? Van der Waals. Now, the other one that we are going to talk about is polar dipole interactions, right? Dipole interactions. Don't confuse London dispersion forces for dipole interactions, meaning they are similar. Intermolecular forces, they are all kind of electrostatic force of attraction between the molecules, right? Now, dipole is when you have like an actual polar compound or molecule. Like if you take hydrogen chloride, for instance, HCl, right? This is polar. And under a normal circumstance, you're going to have the H bonded to the chlorine atom just like this. This is how they are bonded. But since chlorine is highly electronegative than hydrogen, it's going to pull more of the shared pair of electrons to itself, rendering it what we call a partial negative charge, and then the hydrogen being a partial positive charge, right? Now, if this happens, another hydrogen chloride in the vicinity, right, which is also very polar in the first place, that has already gotten its partial positive and its partial negative over here. This partial positive will be attracted to this partial negative will be attracted to this partial positive, and hence we are going to have a bond between them, right? Now, this bond or a force is a force that is between this molecule 1 and the molecule 2 is because of the electrostatics force of attraction, the positive attracting the negative. The compound itself to begin with was polar, very polar. And very polar means that there is a very huge differences in the electronegativity that the compound on an resting phase has taken on partial charges and hence been attracting each other of compounds that are in the vicinity. But for the weak van der Waals forces, it is not necessarily that the atom or the difference in electronegativity is huge. No, the difference is not huge, right? So for that, you have an atom, right, that or a molecule who has, like, let's say, the weak van der Waals forces, you can have like a non-polar covalent bond. It's non-polar, right? And once you have a non-polar covalent bond like oxygen O2, right? If you have this non-polar covalent bond, under normal circumstance, it is oxygen bonded to another oxygen. Now, I'm not really much focused into the bond in between them, whether it's double, single, or triple. Double check it, right? Now, the shared pair of electrons that exist between these two oxygen atoms, right? It's not static, it's not in the middle here, right? It can be found anywhere, right, on either of these atoms, right? So if you found itself over here, this particular atom has become more negative, so more negative. And this being more negative would go and then induce other molecules, right, in that vicinity. So it will come here and then it will induce another molecule in this vicinity. If this is positive, and let's say over here too, we have the similar charges, but its valence electron is nowhere to be found, right? It's, let's say, over here, and this has induced the negative, and this has induced the positive, right? They're going to attract each other. Now, once they do attract each other to form this type of bond over here, they automatically increase the polarity of this molecule, right? And then the chain is going to go on, it's going to go and then attract to other O, and the chain will keep on going on and on. That is lambda dispersion forces, because it disperses through the molecule. Now the dipole-dipole interactions is between molecules that are highly polar already. So the molecule by itself lying there has some polar charges. Now, the characteristic is that this one has a more strength, right? A more force than the weak van der Waals forces or the lambda dispersion forces, and it also has an intermediate boiling point and freezing point whatsoever. The physical properties are intermediate for the molecules that is existing. Finally, we have almighty hydrogen bonding. So 2, 3, hydrogen bonding, right? Now, hydrogen bond, right? If hydrogen is in a compound like water, right? H2O, where we have O, H, H. We have a compound like this, water with hydrogen in it, right? There is already a lone pair of electrons on this oxygen atom over here, right? Hydrogen, since it's a very, very low electronegativity atom, this oxygen will pull the electrons onto itself. So hydrogen itself will be existing as a proton, right? A proton means it has no electron, it will be existing as a proton in this single water molecule. So we're going to have the partial negative here, the partial positive here, and the partial positive here for these two hydrogens, right? Now, as this flows around, the moment it comes across other oxygen atoms, you see it bond to it in the vicinity, right? So you see this one bonds to other oxygen atoms in the vicinity due to the electrostatic force of attraction that exists between the positive hydrogen ion and the negative oxygen atom. Now, hydrogen bonds occurs in these compounds, right? Foam. That is fluorine, right? Fluorine, oxygen, nitrogen. any compound with these, like if you have like hydrogen fluoride, this would form hydrogen bond. Water will form hydrogen bond. And then you have like N, like a compound with N in it, let's say ammonia, would also form a hydrogen bond between the hydrogen and other neighboring nitrogen atoms, right? So now that will be the end of the bonding and then chemical interactions.